Hello, Chem 2 students. Mr. Keister here with you again today. This is the video for Wednesday, October 28th, 2020, which I believe is our scheduled 48th. Yes, 48th day of school for the fall semester. Always keep in mind, though, that the dates could change for a variety of reasons, but the lessons and the order that those lessons are presented will remain the same regardless. So let's take a look at our do nows and see what our schedule is for today. Today we're going to start bonding, all right? Unit 4.1, we're going to start with valence electrons, Lewis dot structures, and then ionic bonding. Your homework for today was to complete Unit 4 Assignment 1. Sorry about that. Unit 4 Assignment 1, turn it in. That is due now. If you're here in class, it should already be on my desk. If you're at home, make sure that you submit that to me electronically by the time your class period begins. All right? Don't be late. And, of course, the answer key you could have checked here in class on the board, or if you're at home, you can check it with the key that is located on the answer keys page in Canvas. All right, so today we're going to begin Unit 4.1, which involves chemical bonding, compound formation, and nomenclature, which is naming, formula writing of ions and compounds. Today we'll start with valence electrons, Lewis dot structures, and ionic bonding, as I said just a little bit ago. We'll get started on the assignment you picked up today. We're going to do parts of it, and then we will finish it tomorrow. Remember again, too, this unit, included in this unit, is the memorization of the names and formulas of 24 polyatomic ions. You picked up the list yesterday, along with a practice sheet. You'll be quizzed over them 3 times over the course of the next 8 school days, with the first time being this coming Friday, all right, which is the day after tomorrow. Make flashcards, use Quizlet, or any method you want. I don't care, but you must memorize them. I will throw out the lowest quiz score. You're going to take it 3 times. I will throw out the low one and average the other 2 for your final grade. All right? There'll be a practice quiz the last few minutes of class tomorrow to see where you're at with your memorization process. I hope you're working on those. All right? A little more involved in memorizing symbols like you did earlier in the year. Okay? Just a little bit more to this. Let's wait for that bell. Sorry about that again. All right. Well, I think let's get on to today's lesson then. And there we go. All righty. All right. So, knowing the electron configuration of an element is important because the number of valence electrons and how far from the nucleus they are largely determine its chemical properties. Remember that valence electrons are those that are found in the highest or outermost principal energy level, and all elements in a particular group of the periodic table have the same number of valence electrons. All right. We talked about that at length in Unit 3.2. So, Group 1A, 1 valence electron. So, lithium, which only has 3 electrons total, is 1s2, 2s1. Sodium, which has 11, 1s2, 2s2, 2p6, 3s1. They both have that 1 valence electron in their S1 orbital, their outermost S1 orbital. Group 2A, of course, has 2 valence electrons. All of the transition metals and all of the intertransition metals also have 2 valence electrons. We've discussed that several times. And then when you get over into the P block, where Group 3A is, Group 3A has 3 valence electrons. Here's an example for Group 4A. So carbon has 6 electrons, 1s2, 2s2, 2p2. Those 2s2 and 2p2, both of those orbitals are its outermost occupied energy level, level 2. That's why it's in period 2, remember? And so it has 4 valence electrons, the 2 s2s and the 2 p2s. Silicon, which is right underneath carbon, 1 s2, 2 s2, 2 p6, 3 s2, 3 p2. Again, it has 4 valence electrons as well, those s2s and p2s. 5a, of course, has 5. 6a, 6. We get to 7a, we have 7. Fluorine, which has 9 electrons total, 1 s2, 2 s2, 2 p5. It's s2p5, or it's 7 valence electrons in energy level 2. Fluorine, which is number 17, actually located right underneath fluorine, 1 s2, 2 s2, 2 p6, 3 s2, 3 p5, and there are its 7 valence electrons. Of course, the noble gases have 8. Their s and p's are all full. Their valence s and p orbitals are all full, of course, with the exception of helium, which only has 2. All right. So let's up here. So valence electrons are usually the first electrons used in the formation of chemical bonds, although they are not always the only electrons used in bonding. Recall that in transition metals, sometimes d electrons in their next most outermost energy level are also used. Same goes with the F's in the F block. In Lewis dot notation or electron dot notation, valence electrons are written as dots beside the chemical symbol of the element to show how bonds are formed. So, Lewis dot structures are basically a simplified version of electron configuration, only now we're only using diagramming its valence electrons, and we're diagramming them as dots. All right. So, for example, in the dots, let me write this down. So the dots are separated, right? The dots are separated around the symbol until all 4 positions around the symbol are used. All right, until all 4 positions have 1 electron around them. And this basically just follows Hund's rule. In fact, it does follow Hund's rule. All right. Okay, so group 1A. So let's see, sodium, potassium, etc. 1 dot only. Now, does it matter? We have 4 places we can put it. Right, left, top, bottom. Does it matter where you put it? No, it doesn't. In fact, if I do potassium, I'll just put it right there. It doesn't really matter where you put the dot. When you start drawing bonding, it's a little more convenient to put it in one place versus another, but there's certainly no requirement as to where it needs to be. Group 2A, such as magnesium, 2 dots, separate, all right? Again, remember, dots are separated until all 4 positions have 1 around them. So here I have them top and to the right. Like here's calcium, which is also in 2A. I could have just as easily had them left and right, or top and bottom, or top and left, doesn't matter, all right? But they do need to be separated. 3A, aluminum. 3 separate dots in 3 out of those 4 positions. Again, you could have used this one and left one of those empty as well. And when you get to 4A, carbon, here is where we have put an electron or a dot around all 4 positions around the symbol. So when you get to group 5A, such as nitrogen, this is where we first start pairing them up, all right? So start to pair up. In 5A. Okay, they start to pair up in 5A. So I'm showing the pair up above the N. I could have just as easily showed the pair on the left, right, or the bottom as well. Doesn't matter. Oxygen is in 6A. It's going to have 2 pairs and 2 singles. There's an example of that. 7A is going to have 3 pairs and 1 single. All right. And then, of course, when you get to 8A, such as neon, we have the S and P's are completely full. We have all 8 valence electrons. The exception, of course, is helium, which only has 2 valence electrons. Now, let's think about that. So, helium has 2 valence electrons, just like 2A does. Now, in 2A, we separate the dots until we get all the way around once. What do you think we do with helium? You think you do the same thing? And if you say, no, we don't, we put them together, you'd be right. And so those 2 dots with helium need to go together. Well, why is that? Because both of those are in the same orbital, all right? So helium, they're paired because both are in the 1s orbital, right? Remember, one's clockwise and one's counterclockwise, but they're in the same orbital. So for that reason, on the Lewis dot structure for helium, we put the electrons paired rather than not paired as they are in 2A. Okay, so make sure you note that difference. All right, so Lewis dot structures came from Gilbert Lewis, right? Gilbert Lewis, who in 1916 proposed that the atoms of the elements react with each other by either transferring, which would be gaining or losing electrons, or by sharing them. The goal is for all atoms to acquire the stable electron structure of a noble gas, which is 8 valence electrons, which would fill their outermost S and P sublevels, their outermost S and P orbitals. This is known as the octet rule. I know Chem 2 students, you have heard that term before in Chem 1. And I'm assuming that even my honors chem students, even though this is their first year in chemistry, have also heard about the octet rule somewhere down the line. All right. So the ideal, we talked about this before, the ideal electron structure scenario is to have those outermost S and P orbitals full, which would be a total of 8 electrons, 8 valence electrons. Octet rule. Of course, the exception to that would be, again, with hydrogen and helium. Since hydrogen and helium are in period 1, they only have an 1s orbital to fill. Helium's is full. So hydrogen wants to have its 1s orbital full just like helium does as well. Okay. But other than that, every other element, we're looking at the octet. Okay. Now, metals, of course, we talked about this in Unit 3 too. Metals tend to lose electrons and form positive ions, or cations, by losing their valence electrons. Nonmetals tend to gain electrons and form negative ions or anions. By doing that, they can fill those. Remember, the nonmetals are in the p block. By doing that, they can fill their p orbital and get to the octet by gaining electrons rather than losing. So today we're going to talk about ionic bonding. Okay. So an ionic bond is the electrostatic, which means opposite charges attract, force that holds together 2 oppositely charged ions, which result in transfer of electrons. Transfer of electrons from between a metal and a non-metal. All right. So this is an ionic bond. By the way, chemical bonds are called intra. We're going to introduce that term because we're going to talk about it a lot more in a couple of days. Bonding is an intramolecular force. Intramolecular force. Forces within a molecule. Found force within a molecule that holds it together. Okay. So the strength of an ionic bond is determined by the difference in the electronegativities of the two elements involved. The greater the difference, the stronger the bond. All right, so we talked about electronegativity in Unit 3.2, and you picked up today an electronegativity chart. We had a similar one back in Unit 3.2 when we were studying trends. This one is a little more updated, all right, and complete. So if you look, all you see here on the electronegativity chart is the symbol of the element. Up above it is its atomic number, and then below it is its electronegativity. All right. Now, if you look closely here with me, in this upper right corner where the nonmetals are, all right, there are several there that are very dark. And so it's difficult to see the number. And so what I did is I wrote them here around the perimeter so that you could tell what they were. And so make sure you refer to that. The only other one that people seem to have a little trouble deciphering is silicon, which is right there under carbon. Kind of hard to tell if it's 1.90 or 1.80. It is actually 1.90. So you might want to write that in. If you can't already tell for sure that that's what it is, all right? 1.90 for silicon. All the rest of them I think you can read without much difficulty. But again, I did these around the perimeter here because they were pretty hard to read because of how dark it was, all right? So electrons are transferred from the lesser electronegative element, which are metals. Of course, they have very small electronegativity, to the greater electronegative element, the nonmetal. So here's the magic number right here, little star there. A difference in electronegativity between two elements that is 1.67 or greater indicates that an ionic bond will form between them, all right? 1.67 or greater. The compound formed by the transfer of electrons between a metal and nonmetal and the resulting electrostatic attraction of positive and negative ions is then called an ionic compound. So ionic bonding yields ionic compounds, right? Same name, right? So general properties of ionic compounds. Most are crystalline solids at room temperature. Well, if they're solids, what does that tell you about the force between them? All right, solids particles are very close together, right? Which then means I would say the attractive force between the particles must be pretty dang strong. Well, it is, all right? Ionic bonds are very, very strong, all right? And so that's why most all are solid at room temp. They conduct an electric current when melted or dissolved in water. So you put them in the liquid phase by either melting them or dissolving them in water. Then those water wedges itself in between those ions and splits them apart. We'll talk about water a lot in the coming days. And those positive and negative ions that make up that ionic compound are separated. And so when you have charged particles roaming around freely, that is conducive then to conducting an electric current, right? In fact, that's what electricity needs is positively charged, or I should say, charged particles to send the electric current from one place to another. It needs a charged particle to do that. They're very stable compounds. They have extremely high melting points. Now, this is why, again, ionic compounds are solid, all right, because that bond is very, very strong. It takes a lot of energy to break it, to get those particles apart so that they go into the liquid phase, and thus they have very high melting points, all right? So, for instance, sodium chloride's ionic melting point is like 800 plus degrees Celsius, which is close to 1500 Fahrenheit, all right? That's a pretty high temperature, all right, for melting. All right, remember, water, ice melts at 0 Celsius. Sodium chloride melts at 810 Celsius. Big difference there, all right? So they're very stable compounds, very high melting point. All right, so let's look at some examples of ionic bonding and the formation of ionic compounds. All right, so I'm going to show you a very specific way in which these bonds are drawn and then how you draw the resulting compound's structure. Okay, So let's scoop this up here. So first things first, we need to remember that if the electronegativity difference, so the EN difference is greater than or equal to 1.67, then we have an ionic bond. So first things first, we're going to check the electronegativities of these, although we know now they're ionic. I want to verify that because when we come to where we have compounds all mixed up together, you need to be able to tell what bonding occurs between them. So if we look up sodium, I'll just write it above its symbol here. So sodium is 0.93 and fluorine is 3.98, I believe. Yes. The difference between those, you just take the non-metal first minus the metal, so we get a positive answer. 3.05, which is much, much higher than 1.67. So they're going to bond ionically. So let's draw the Lewis structure for sodium. It's in 1A, so it has 1 dot. Fluorine is in 7A, so it's got 7 valence electrons, or 7 dots. Now, does it matter where you put the single? No. Does it matter where you put the single in sodium? No. But here again, when we're drawing bonding, it just becomes a little more convenient to line up the singles apart from each other because that's where the bonding is going to take place. All right? So, what happens here? We said the lesser electronegative element transfers electrons to the more. That means the metal is going to lose its electrons to the non-metal. Well, how many electrons does sodium want to lose? And the answer is 1. Then, how many electrons does fluorine want to gain? And the answer is 1, which means then that these two are going to bond ionically in a 1-to-1 ratio. Sodium wants to lose 1, fluorine wants to gain 1, so they're going to bond 1-to-1. We draw an ionic bond as a single pointed arrow, one directional arrow pointing to the receiver. The receiver is the non-metal. So just like so. And then over here, it's Lewis structure, which is the structure of the compound. We also call it a structural formula. You'll see both of those terms. They mean the same thing, right? I tend to use Lewis structure, but structural formula, same thing. Okay, we're now going to show that fluorine has picked up that electron from sodium. So now it has its 8 valence electrons, but it's not neutral anymore. It was neutral when it had 7 valence electrons. When it picks up an electron, it now is a negative charge, in particular -1. So you can either write -1 there or negative, I don't care, because either one is correct for -1. Sodium has lost its valence electron, all right? And so it's now positively charged. And so I'm going to write +1 next to sodium. You could also write just plus since it's only 1. But as you can see, we're showing now those particles are charged, which they indeed are, all right? So this would be the Lewis structure for NaF. Now, when you write a chemical formula, like you see in an equation or whatnot, we take the Lewis dots and the charges out of it. So if you would just write a formula like in a reaction, you would just write NaF, since there's 1 of each. All right, and the positive one, the metal's always written first. But that's for later on down the line. That should be review. You guys should know that anyway. All right, so let's look at number 2, barium and chlorine. All right, so barium's electronegativity is 0.89. I'll write that above it. Chlorine, 3.16. So we find the electronegativity difference there. 2.27. Again, greater than 1.67, they're going to bond ionically. So barium has 2 valence electrons. And remember, we showed those dots separately, not together. All right. Chlorine, again, has 7. So 3 pairs in a single. Again, I'm just putting the signals across from each other, so it's easier to draw the arrows. All right. Okay, so they bond ionically. Now, chlorine only wants to gain 1 electron, but barium wants to lose 2. So if barium loses 1 of these electrons, that's going to fill chlorine's octet. But that's not, barium's not happy about that. It wants to lose a 2nd electron. And so for this reason, barium and chlorine, unlike sodium and fluorine, do not combine in a 1-to-1 ratio, but instead they combine in a 1-to-2 ratio. So now we have a 2nd chlorine, and now barium can lose its 2nd valence electron to that 2nd chlorine atom. So they combine in a 1-to-2 ratio so that all the atoms involved here achieve their octet. Now, when we draw its Lewis structure, all right, so let's look at that. So the barium has lost 2 electrons. So now it has a charge of +2. Again, you could write it 2+, all right? And each of these chlorine atoms now has a -1 charge because they each gain 1 electron. So I'm going to put one of them over here. 1, 2, 3, 4, 5, 6, 7, 8, -1, or just minus. Now, before we put the other one, I want you to think about it. Here I'm showing that other chlorine atom right next to the other one. But when they're charged, they both have a -1 charge. They're going to be wanting to be right next to each other? No, not at all, because like charges repel. So where could you put the other chlorine ion so that it's still close to barium, because it's attracted to that positive charge, but it's far away from the other chlorine as it can be? And if you sat over here on the other side, you'd be exactly right. So put a little note here. Keep like charges. Keep like charges as separated as possible. Why? Because they repel. They're both attracted to barium, so they want to be close to it, the barium ion, but they don't want to be close to each other. So the farthest apart they could be is on opposite sides of that barium ion, and that's exactly where they are. All right? Now, if I was just going to write the formula for this compound, like on an equation, it'd be BaCl2, all right? Where we have 1 barium ion and 2 chlorine ions, which would be right there. One thing I wanted to note here is, you notice we wrote both chlorine, in our Lewis structure, we wrote both chlorine ions separately. You notice we didn't write it like this. We didn't do it like that. You say, well, I could save some time and just put a 2 there, -2 there, and that shows there's 2 of them. Well, no, it doesn't. Look at it. We're showing a barium ion with a charge of +2, which is correct, but now we're showing 1 chlorine ion with a charge of -2. Is that what we have? And the answer is absolutely not. So if you think you can shortcut the drawing by doing that, well, you could, but it's wrong. All right, it's wrong. Okay, remember that. Okay, third one, lithium and nitrogen. Lithium is 0.98. Nitrogen is 3.04. Subtract that one. 2.96, I believe. Or 2.06. Jeez. My math's not too good there. Not good. 2.06. Still over 1.67 though. And so definitely ionic. So if I draw a Lewis dot structure for lithium, it's got 1 dot. Nitrogen is in 5A. So it has 5 valence electrons. Remember, that's 1 pair. I'll put it over here, and 3 singles. So as you can see, lithium and nitrogen aren't going to bond in a 1-to-1 ratio either. Lithium will lose an electron, of course, to nitrogen. It'll pull it away. And that lithium is now happy because it's achieved its octet. The nitrogen wants 2 more electrons. So when these two elements come in contact with each other, we're going to add not only a second, but a third lithium. And they're going to combine in a 3-to-1 ratio. 3 lithiums to 1 nitrogen. All right. So our Lewis structure then. So here's our nitrogen ion, which has gained 3 electrons. So it's got its octet, but it now has a charge of -3 or 3 minus. All right, because it picked up 3 negatively charged electrons. So now where are the lithiums going to go? Again, well, they're all attracted to that negative ion, that negative nitrogen ion. Let me erase that. So I'll put 1 here. So Li plus 1 or Li plus. Where are the other 2 going to go? Well, what's the farthest apart they can be? And if you can kind of visualize the triangle, you'd be right. So that's basically the maximum distance that those lithiums can be from each other, while yet being as close as they possibly can be to that nitrogen, that negatively charged nitrogen ion. All right. So it would look something along those lines. Okay. Of course, you could rotate those somewhat, but basically the triangle there. If we were writing just its formula in an equation, it'd be Li3N. All right, just FYI, Li3N. All right, and then finally, aluminum and oxygen. All right, I think I'm going to erase here so we have some more room to work with. We got all that down. Let's raise this up. There we go. All right, so aluminum 1.61, oxygen 344, I believe. Yes. And we subtract those. See if I can do a little better on my subtraction. 183, I believe. 1.83. Yep, that's right. So again, it's ionic. So let's look here. So aluminum has 3 valence electrons. It's in 3A. So 3 separated dots. Oxygen's in 6A. So it's got 6 valence electrons, which would be 2 pairs and 2 singles. All right. So oxygen's going to take electrons from aluminum. It's more electronegative. So we'll send one of aluminum's there and the other one there. And that first O has achieved its octet. Aluminum has not. So they're not going to combine 1-to-1. So we got to get rid of another electron from aluminum. So we're going to have to use another O. And I'll send it there. Well, now the first aluminum is good, but the second O is not. So now we're going to need a second aluminum. And we'll send its first electron to that second O, which has now achieved its octet, but the second aluminum has not. So we're going to need yet a third oxygen. I'm going to have to draw it down here, sorry. And now if we send aluminum's last 2 electrons, or that second aluminum's last 2 electrons to the third O, I believe everybody now has achieved their octet. So now aluminum and oxygen, as we can see, combine in a 2-to-3 ratio so that all the atoms achieve their octet. All right. So Lewis structure. Well, we have an aluminum that's got a +3 charge, or a 3+ charge, and we have 2 of those. And we have 3 O's, all with a -2 or 2- charge. So how are you going to write that? Remember, we want the positives separated from each other and the negatives separated from each other, but the positives and negatives close together. Well, how about this? What if we just line them up? And I guess that would put this one out here. Again, each of those oxygen ions have a -2 charge, or 2 negative, because they gain 2 electrons. Each of those aluminum ions lost 3 electrons, so they each have a +3 or a 3+ charge. And so if you line them up just in a straight line, negative, positive, negative, positive, negative, you minimize the repelling between like charges, but you maximize the attractive forces between positive and negative. All right? All right, so I think that is, so I guess its chemical formula then, if we were going to write it down, would be Al2O3. Remember, when writing a formula, all right, when writing a chemical formula, we take the dots and the charges out for ionic compounds. The metal or the positive ion is always written first in a chemical formula, followed by the non-metal ion. All right, so metal first, non-metal following. Okay, that's the way you always see it in an equation. That's the way you always write it. And again, in a regular chemical formula, the dots and the charges for ionic compounds are removed. Okay, well, let's look at our assignment. All right, so our assignment, let me grab one real quick. All right, so here's our assignment entitled Ionic and Covalent Bonding. So we covered ionic bonding today, all right? So as you can see, let's look at the instructions together. For each of the following compounds, use the periodic table and the table of electronegativities as guide 2. Out in the left margin, use the table of electronegativities and show work to identify the bonding as either ionic or covalent. Then write which type it is in the space provided. So just like you did up here on our examples in the notes, you are to do the electronegativities, record them. Above each symbol is fine. And then out in the left margin, do the subtraction to show what type it is. All right? And then if it's ionic, we're going to write ionic in the blank under type of bonding. Then draw the Lewis dot structure for each atom and then diagram how the bonds are formed. So we have done that right here. All right, so we've done the Lewis dot structures and drawn the arrows to show the bonding all in the same place. So that would be done under the drawing and diagramming part. And then over on the far right, the last column, the Lewis structure is what we have right there. So what I want you to do for this assignment is to find all the ionic compounds, all right? So you can do all the electronegativities, do all the subtractions. Let's see how many we got here. There's 14 of them, okay? And then if it's 1.67 or greater, it's ionic. If it's less than 1.67, what's it going to be? Well, it's going to be covalent. Now, we haven't talked about covalent structures yet. We're going to do that tomorrow. So what I want you to do for tomorrow is on this assignment, do the electronegativity difference and the type of bonding for all 14, all right? And then for the ones that are ionic, I want you to complete them, all right? Draw the Lewis dots and diagram the bond formation, and then draw the resulting Lewis structure. So do that just for the ionic compounds, all right? Got it? All right. That takes care of today's lesson over ionic bonding. So until next time, this is Mr. Keister signing off. Stay safe, everyone. Take care. Keep after it. Stay focused. Keep working hard. And don't remember, work on those polyatomic ions too. In fact, we have a practice quiz, I believe, tomorrow. So don't forget about those. Be working on those as well. So until then, take care, everyone. See ya.